Let's take a look at a complete walkthrough of solutions to free response question 6 from the 2025 AP Calculus AB exam. This is the last problem on the free response section of the exam, and it's all about implicit differentiation. So if you've got all of your usual differentiation rules for finding derivatives locked in, there's just one little extra step you need in order to apply them all successfully for implicit differentiation. So this is a great one to be practicing because implicit differentiation comes up every single year. Let's dive in. So for most of this problem, we are working with a curve g defined by the implicit equation y cubed minus y squared minus y plus a quarter x squared equals 0. Now on the exam, we won't really have any idea what that looks like. This is non-calculator, so we can't even mess about there. But since we're working on this together today, I've plotted it in Desmos just so that we can be looking at it together and have some intuitive feel for what's going on. The great thing about calculus, though, is hopefully you're discovering you don't need to have a picture of the graph to be able to work out really concrete things about this curve. You can use the tools that we're developing in calculus. So, pretty nice. So in part A, they're asking us to basically find an expression for dy by dx for this curve. Now, they're asking us to verify it, so they're giving us what dy by dx is, because as we'll see in later parts, B and C, we are going to work with that equation. So they don't want to penalize us if in part A we're not able to actually calculate dy by dx. We can still use it to figure out slopes of tangents, that sort of thing, in later parts. But for now, they're asking us to actually try to find it. So for conventional explicit differentiation, typically, right, what we do is we have an expression y equals some, we have a rule, y equals some expression in terms of x, say f of x. And then we use our differentiation rules, or maybe first principles, to work out what dy by dx is equal to. But here, that is not the setup that we have. Okay, this implicitly defined curve would be really tricky to try and solve for y. In fact, it might even be impossible, like in this case. Okay, so in this sort of instance, to find dy by dx, we need to use implicit differentiation. So all we're going to do is we're going to take both sides of the equation and differentiate with respect to x. So I'm going to apply d by dx to the left-hand side, and I'm going to apply d by dx to the right-hand side and see what we end up with. Okay, so when I do that, well, the right-hand side is easy enough, right? Because it's a constant, so d by dx of 0 is just 0. And now that left-hand side, just like with explicit differentiation, I'm going to differentiate each additive term as I see it. So you can see I have 4 terms, all added or subtracted together. I'm going to take each term in turn. If the term is purely in terms of x, like that last one, I'm just going to take the derivative with respect to x like normal, okay? Like in this situation here that I've crossed out, that term by itself is just purely in terms of x. I can differentiate d by dx, no problem. When I see a term involving just y, okay, really we're assuming that y is at least partially dependent upon x, and so there's some kind of chain rule going on in the background. You don't need to know this or remember this, but that's really what's underpinning implicit differentiation here. So what we're going to do is treat those terms like we're applying the chain rule. So I will differentiate each term involving y with respect to y, like that's the derivative I'm taking. I then just need to remember the chain rule requires me to multiply by the derivative of y with respect to x. Let's see what I mean. So for this first term, this y cubed, if I differentiate that with respect to y, I get 3y squared, easy. But I'm not differentiating with respect to y, I'm differentiating with respect to x. So I need to remember to multiply by the derivative dy by dx. And that's what we're going to do for every single one of these y terms. So minus y squared will become minus 2y. Need to multiply by, dy by dx. And that minus y will become minus 1 times dy by dx. Then I get to that nice purely in terms of the x term, x squared will give me 2x as a derivative, and so I get plus x over 2, because the 2 cancels with the 2 in the denominator. Okay, so now we just need to verify that dy by dx equals this expression they given me. So in this sort of problem, what you're going to want to do is factor out the dy by dx from every term that has a dy by dx. Okay, so what terms have dy by dx's? Well, it's this one, and this one. So when I factor out there, I'll get 3y squared minus 2y minus 1, all in my parentheses. What about the terms that don't have a dy by dx? In this case, the x over 2. You're going to shove those onto the other side of the equation. So I'll get negative x over 2. Now you can see why have I done this? Well, to solve for dy by dx, I can just divide by the terms of the parentheses. So I will end up with dy by dx equals, okay, I've got negative x in the numerator, I've got that 2 in the denominator, and then this quadratic polynomial in y, I'm just going to divide down to the other side. So I'll get 3y squared minus 2y minus 1 as required. That's what we were looking for. So we're done. How were the points divvied up here? Well, we get 1 point for our correct implicit differentiation step. And then we get 1 point. Actually, the point we get is sufficient to just stop here. Right, we're done with our calculus steps. That's just some basic algebra rearranging, okay? They're not going to want to give you a point for copying down what they have given to you in the statement of the question. That would be strangely generous, okay? So as soon as you get to that intermediate step, you're done, you can pull the plug. But if you want to just double check your work, make sure that you do end up with the correct expression. It doesn't hurt to take the extra 10, 15 seconds. To verify that your algebra gets the same answer as theirs. Okay, on to the next part. Okay, part B, you can see I've copied in the expression that they gave us for dy by dx because we are going to need to use it in this part B, regardless of whether or not we actually found it successfully in part A, right? They gave it to us for free. How nice. Okay, so in this problem, we are given a couple of points on the curve. So we're looking at the point 2, negative 1. So that is right there on my curve. Again, in the problem, under exam conditions, we wouldn't have this curve. We'd have to do it mentally, but conceptually, there's no difference. Okay, and we want to find the y-coordinate of a point nearby. So let me zoom in for a second, as far as I can. Okay, so we are looking at the point x with the x-coordinate 1.6 that is nearby. So that is 1.6. I want to figure out what the y-coordinate is for this point. Okay, or I want to at least estimate it, right? We can see it's a little bit closer to 0 than negative 1, but I'm not sure exactly what it is. And we're told to use the tangent line to the curve at this point, 2, negative 1, to approximate the y-coordinate of this second point when x is 1.6. So how's this going to work? Well, conceptually, right, if I have my tangent to the curve passing through this purple point, okay, it's going to be something like that. So when I actually sort of marry that tangent up with the curve, you can see, okay, it pretty closely estimates what the curve is doing, but it starts to deviate a little bit, right? The curve is curving, the straight line is staying straight. But you can see around this point here, when x is 1.6, the tangent line, straight line, and the curve are behaving very, very similarly. So I can use the equation of the tangent line to approximate the y-coordinate of the curve at that x value. That's conceptually what's going on here. Let's zoom out and see how we're going to tackle this. So we want to find the equation of the tangent at the point 2, -1. So we've got a point on the curve, 2, -1, a point on the tangent. We need to find the slope. And that is where this expression for dy by dx comes in. Okay, I need to substitute in the xy value that they have given me. So 2 and -1. So if I substitute in here, I'll get negative the x value all over 2 times, okay, I'm doing 3 times -1 squared. That's 3 minus 2 times -1. That is 2 and then -1. So if I simplify this, what I will end up with is -2 over 8. That is -1/4. So the slope of this tangent line that I'm looking at is -1/4. So if I write down the slope of the tangent, or the equation of the tangent line, it's going to be y minus the y coordinate of my point equals the slope times x minus the x coordinate. So y is going to be -1/4 x minus 2 and then subtract 1. Okay, just solving for y. So what we're going to do is we are going to substitute x equals 1.6 into the equation for the tangent line, and that will give me an approximation of the y coordinate of the point on the curve G. So y is going to be approximately equal to -1/4 times 1.6 minus 2 minus 1. If we work out exactly what this is, we should get -0.9 as our answer, which, as we saw from our graph, which remember we wouldn't have on the exam, but here we can compare, that is roughly what we were expecting here as our answer. Great. So how were the points divvied up here? Well, we get 1 point for figuring out the slope of the tangent line is -1/4, and then we get 1 point for the final approximation as long as we definitely used the equation of the tangent. Okay, we weren't allowed to approximate using some other method. We had to use this idea of estimating via the tangent line, via a linear approximation. Okay, good job. On to part C, where we're being asked to find the y-coordinates of the points on the curve that have vertical tangent lines. Okay, so again, I've copied in the expression for dy by dx because we're going to use that in this part. Okay, so vertical tangent means the slope is undefined, right? Vertical tangent means slope undefined. So if I look here at my expression for dy by dx, it's lots of things, but in particular, it's a fraction, okay? So how could that fraction not be defined? Well, I might try to divide by 0. The denominator might be 0 for some particular I values. So we want the slope to be not defined. So what we need is this fraction for dy by dx to be of the form a number over 0. Okay, a finite number over 0. We can make this more precise with limits if we want to, but in terms of this sort of expression, if I find something that looks like a finite number trying to be divided by 0, I know that that is going to give me an undefined infinite slope. Okay, so that's nice because that tells me, I just need to solve when that denominator is going to be 0. Okay, the 2 can't make a difference, but the y's sure can. So now I could solve, I could factor this. That's the most surefire way to do this, just by inspection, by trying to split that middle term, standard. We could try plugging in some y values, okay? But however we solve this equation, that's all we have to do. So I'm going to get 3y plus 1 times y minus 1 is equal to 0. Okay, if we want to verify this is correct, right, we'll get 3y squared minus 2y minus 1. Just using FOIL to expand those brackets out. Great. Okay, so using the zero product property, this tells me that y is either negative 1/3 or y equals 1. So I've got my two possible solutions. Ah, great. Not quite done though, because one fact I glossed over is we need x and y to both be strictly positive. Okay, so this solution here for y is negative 1/3, not a correct solution. If we include it, we won't get full credit for this part. Okay, so we are actually done. Okay, so we need to see how the points are divvied up. Right, good practice. So we get 1 point for knowing that we have to solve the denominator being equal to 0, and we get 1 point for our final answer, as long as we remember to throw away that 1/3, that negative 1/3 solution. Okay, so if we look at this on our graph that we wouldn't have access to on the exam, but here, where do I see my vertical tangents? Well, I have vertical tangents here and there. Okay, I don't see any other vertical tangents, but importantly, yes, great. The y-coordinate of those points with those vertical tangents is y equals 1. Technically, we were only interested in this right-hand one because we also wanted x to be strictly positive as well, but that's neither here nor there. Nice. Let's move on to the final part. So this final part, part D, is probably where you're going to sweat the most and put in the most effort. There's 3 points up for grabs. Let's see how we're going to obtain them. Now this curve G is out. We're not looking at that anymore. We're being given a different curve. It's still defined implicitly. It's 2xy plus ln y is equal to 8. Again, we wouldn't have an idea of what this looks like on the actual exam, but since we're here today, I've plotted it in Desmos for us. So it's this sort of nice looking decaying curve, okay? And there's a particle moving along this curve, okay? Usually particles for us move along x-axes, straight lines. Today it's curving things up. Okay, so when the particle is at the point 4, 1, so this point right here on the curve, let me zoom in for a second. Okay, we're told that the horizontal rate of change, okay, it's horizontal velocity in some sense, is dx by dt equals 3. And they want us to work out what dy by dt is at that point, okay, at that moment in time. So you can see if I'm moving to the right, I better be moving down. If I'm going to stay on that curve, okay, dy by dt had better be negative. Okay, the y value better be decreasing in time. And you can see if I don't perfectly pitch dy by dt at the right speed, my vertical velocity, I won't stay on the curve. Okay, there are lots of ways that I can travel to the right at a rate of 3 units per second. And if I don't travel with dy by dt at just the right rate, then I won't stay on the curve. So this question is really asking us, when I'm moving to the right at 3 units per second, how quickly do I need to move up and down to make sure I stay on this curve? Okay, because remember, the particle is constrained to be moving on that curve. So that's what's going on conceptually in this problem. Well, I know dx by dt and I want to find dy by dt. So what we're going to do is implicitly differentiate this new equation that they've given us, okay? But this time, I'm going to differentiate with respect to time, d by dt, because those are the rates I'm interested in. It's a rate with respect to time. So it is, again, implicit differentiation, following the same steps, the same procedure, but just with a little twist, because this time I'm doing a d by dt derivative, not a d by dx derivative. Let's see how it's going to go. So I'm going to take a little extra step here and say, okay, I'm going to differentiate both sides with respect to time. That right-hand side is a constant. 8 isn't changing in time, so that's going to be 0. That is nice. Again, for that left hand, side of the equation, because it's two terms added together, I can take each term in turn. So I'm going to do d by dt of 2xy plus d by dt of ln y. Okay. Now, previously, what was the philosophy? Every time I wanted to take a derivative of a variable that wasn't my independent variable, last time it was x, this time it was y, I had a strategy, right? I take the derivative as if I'm working with the variable in question, and then I just need to remember to multiply by the derivative the chain rule tells me to do. Okay, in this case, it will be d by dt. So let's look at each term in turn, and hopefully you'll see what I mean. So let's do the second term, because it's a little bit more straightforward. So if I was taking the derivative of ln y with respect to y, oh, that would be super nice. That's a standard derivative. Ln of y would differentiate to 1 over y. Standard derivative. And that's what we're going to do here. Okay. But implicit differentiation, chain rule tells me I need to multiply by the derivative of y with respect to the variable I'm actually working with in my derivative. It's dt, right? 1 over y times dy by dt. Let's make that equal to 0. d by dt of 8 is 0. What about that first term? Well, it's a little bit more tricky, but it's still totally the same strategy, same process. Why is this trickier? Well, it's a product, right? X is multiplying with y. So I need to apply the product rule. So let's see how that's going to go. So let's have each factor in turn. So I pull that 2 out the front. I've got my x factor and my y factor. So my version of the product rule says take the derivative of the first factor. So x will, if I was differentiating with respect to x, that would give me 1. I then need to multiply by dx by dt. So that is what my first factor is giving me. I leave the second factor alone, right? So that was just y. And then the product rule tells me to do that in the reverse. So leave that first term alone, x, and then take the derivative of y with respect to t. So my process says, pretend I'm taking the derivative with respect to y. That would give me 1, but then I need to remember to multiply by the derivative dy by dt. So that is the end of that first term. And it's actually the end of all of our calculus, right? We've done all of our derivatives. And now you can see I have this really nice expression. What have I been asked to find? I've been asked to find dy by dt. So I see I have an equation involving dy by dt and a load of other terms that I'm actually going to substitute in for, right? Because I know what dx by dt is. I know what y is. Y is 1. And I know what x is. X is 4. So we can just substitute in now and rearrange to solve for dy by dt. We could rearrange first, but that's a lot more symbols. I'd rather get rid of the symbols, replace them with their constants, and then solve from there. Okay, so we're going to substitute in x equals 4, y equals 1, and yes, dx by dt equals 3. So what do I get? I have that 2, 1 times dy by dx, which is 3, times y, which is 1, plus x, which is 4, times 1, times dy by dt. That's the expression, that's the value I want to find. I then get plus 1 over y times dy by dt, and that's all equal to 0. Let's keep pushing. So that's going to give me 2 times 3 plus 4 dy by dt plus 1 dy by dt equal to 0. So that is 6 plus 8. Oh, but I have that extra one, right? So that's really 9 dy by dt equal to 0. So if I solve for dy by dt, I will get negative 2/3 as my answer. Amazing, we're done. So how were the points divvied up here? I said there were 3 of them available, so let's see. Well, we get 1 point for attempting implicit differentiation with respect to t. Okay, so something like this first line where we attempt our implicit differentiation, we know that we're supposed to do that. Maybe we don't necessarily do it entirely successfully. We'll still get 1 point for the attempt. Great. We then get a second point for actually completing the implicit differentiation successfully. Okay, so using that product rule correctly, differentiating the ln of y term successfully. All good. And then we get our final point for actually substituting in and solving for our answer of dy by dt. And that's it. So great job. How did you get on? Let me know in the comments. I would love to hear from you. That final part was probably the most work because of that product rule happening inside of the implicit differentiation, but I would love to hear your take. If you've been working this exam in order, congratulations. This was the last free response question. Great job. If you haven't tried the other free response questions in the 2025 exam, I'll put a link to my complete playlist where I run through them one at a time here. If you're in the mood to practice some multiple choice questions, I'll put a link to that playlist right here. And apart from that, I will look forward to seeing you in my next video where we'll start a new exam fresh from scratch. Bye.